Chapter 11, Angular Momentum. Angular momentum symbol is capital L. Before, let's begin with the linear momentum. If we have a small object with a mass m has a velocity v, in this case, the linear momentum here is lowercase p, which is equal to m times v. P is a vector quantity. In the case of a rotational motion, let's say we have a disk. This disk has the ability to spin around the axis. We have a vertical axis here, and we have a angular speed omega. The object has a mass m. Here we talk about the angular momentum L. L, which is equal to I times omega. We have a big similarity between this expression and this expression. I is the moment of inertia. The moment of inertia is the rotation equivalent of the mass m in this equation. Omega, the angular speed, is the rotation equivalent of the velocity v. L is the is the angular momentum, the rotation equivalent of the linear momentum p. Okay, second equation. We have, in the case of linear momentum, summation of f equals to m times a. And a equals to dv divided by dt. M is constant, we can put it inside. We get dp divided by dt. This is a simple relation between f and p. In the case of rotation, here we talk about tau. Summation of tau equals to I times alpha. At a certain moment, alpha equals to d omega divided by dt. I is constant, so we can put it inside. We get here d divided by dt times I omega. I omega equals to L. So summation of tau equals to dl divided by dt. We have a similarity between these two expressions. Okay, now let's talk about the conservation of angular momentum. Here we have, in the case of isolated system, if the summation of f external applied on the object, which is equal to dp divided by dt, in the case of isolated system, it means the summation of f external equals to 0. Okay? So we don't have a changement of linear momentum. So P is constant. We can say P initial equals to P final. Okay? The same, we can say the summation of tau external, which is equal to dl divided by dt. If the summation of tau external equals to 0, in this case, we have an isolated system. So dl, L is constant in this case. We can say L initial equals to L final. So we can say directly here, in the case of isolated system, we have a conservation of mechanical energy initial equals to mechanical energy final. Also, summation of F external equals to, you can say here, we can say we have P initial equals to P final, and we have L initial equals to L final. Also, we have an isolated system when the summation of F external equals to 0 and the summation of tau external equals to 0. This one gives us this relation, and this one gives us this relation. Okay, now let me give you the general expression of the angular momentum. In general, L must be equals to R cross P. This is the general expression. Let's take here a simple example. Here we have a mass M. We have a rotational motion about the axis as a point O. This object has a mass M and a velocity V. So in this case, we can say the linear momentum P, which is equal to M times V. P takes the same direction of V. Here we have P. As we have a rotational motion, in this case, L of this mass must be equal to I times omega. Okay? Let me solve this relation to get this result. First of all, here, I will find the magnitude of L. Okay, I just talk about the magnitude. Here, R times P. The angle between R and P equals to 90. So we have R times P times sine 90, which is equal to 1. So R equals to P equals to M times V. And we have a rotation with angular speed omega. We have a relation between V and omega. V equals to R times omega. We can write here R times M times R times omega. Here equals to M R square times omega. Okay, this is the magnitude. What about mr square? Let me calculate I of the mass m. In general, I equals to I cm plus md square. As the axis is not passing through the mass m, so we don't have ACM. D is the distance between the center of mass of the mass m and the axis, which is equal to r. So here we can say I equal to mr square. So we can write here equals to I times omega. This is the right answer. What about the direction of L? Here we can follow the same procedure like the torque tau. We have to use your right hand rule. We put your finger in the direction of R. P must be out of your palm. So we get L must be out of the page with your finger, okay? Must be out of the page. We can say in the direction of J, plus J. So here we can write L, which is equal to I omega times J. Later, in the next videos, we can have some application to understand very well the application of this relation.